This is lecture 10 called Composition of Functions. It's a pure math course called Finite Group Theory at junior and senior level. The first author of the text is Barnard, and here's the text. It's in the Teach Yourself series, and the title is Mathematical Groups. Now, from the previous lecture, we learned all about functions, so we have a pretty clear idea now what a function is. So this lecture is a kind of extension of the previous one. And the basic idea is you're talking about more than one function. So in a sense, you have a function that has parts, and those parts are other functions. So here's an idea of what we're talking about. Now, before we were mapping from one set, say A, to set B. So this would be the domain, and this would be the codomain. Okay. Well, now we've got three sets, and we're mapping twice. So we have one mapping F, and that's a function. It's a properly well-formed function. And then we have a second function, G, which is also a well-formed function, a proper function. And what happens is that F maps little a from your domain to this member B of your codomain of big set B. And then we have a second function, G, here, which takes that element B and maps it to a third element, C, in this third set. So in a sense, this middle set here, on the one hand, it's the codomain of F, but in another way of speaking, it's like a dual role, if you like, has two jobs. It's the domain of this function G. So this set here, big C, is in effect a second codomain, right? So we have this sort of composite or having parts function that we could call H. So you've got function F, function G, and this is function H. And what it does is it takes any element in set A, the original domain, if you like, and maps it directly onto an element of C. Okay, so so this function H takes any element A belonging to your set big A, right, and maps it to C via two steps. So it's like a two-step process. So to get from A to C, you do a two-step process. First you map using F, the function F, to take you to little element, well, to element little b, and then a second function G that maps you to element little c. Okay, so here's what's going on. So H in effect is a double-barreled function. It's like well, F applies first. Now I should point out here that you're applying two functions one after the other. So be careful with the order. Now the convention is that the first function you put closest to the first element that you map. Right? Now we're mapping little a here, mapping that one, and so it'll be F that maps it. So F maps little a onto B. Right? Here it is here, and then function G maps B to C. So function G here maps B to C. Okay, so so this double-barreled. First you do F, then you do G. You write it as GF, not FG. Okay, why? Because, as I just said, the first function is closest to your original element. Right? So F operates on A first. The result is then B here, right? And then G operates on B to map it to here, to little c. Okay, so that GF here, this GF, which is H, so that means this H here has parts. It has two parts, two functions, and this H is called a composite function. Anything composite in English just means it has parts. Okay, if something is composed of something, it means you build it up from smaller parts. Okay. like a composer in like Beethoven or Mahler, or right? They make music by putting together notes, in a sense. So they compose the music by putting notes together. So here you're making a composite. You're composing a function, if you like, h, by using parts f and g in that order. First f, then g. Okay, so from right to left. Don't forget the order, otherwise it gets confusing. All right. So we have now quite a few theorems. So this lecture risks to be rather long. So I'll break it up. And I'll have to clean the board several times anyway, probably. So how many theorems do we have for this lecture? So 1, 2, 3, 4, 5, 6, 7. 7 theorems. So many pieces. Okay. All right, so I'll start with theorem 28. And I think from memory it's about proving that this is a well-defined function. Now, a bit of revision from last lecture. Can you remember what a function, how do you define a function? It has 3 parts. If you're a bit rusty, go back to the previous lecture, what would that be? Lecture 9. This is lecture 10, so we're right now in the middle of this course, because there are 19 lectures. Okay, so how do you define a function? Well, it has 3 parts. Revision from last time. You have a domain, a starting set. You have a codomain, that's like a target set. And you have a rule, in this case f, and that rule takes an element, in fact it takes one element at a time in a sense, and maps it to just one element in the codomain, or the target set. Okay? And this rule, this function, maps every element of your domain. That's important. Right? If it doesn't map every one, it's not a function by definition, in this mathematical definition. Okay? So it maps every element, every member of your starting set or domain into uniquely just one element of your codomain or your target set. Okay? So to prove that this h, and this is what theorem 28 is about, it's asking you, well, here, I'll just read it out. Okay, so you're given that you have f which maps a to b. So alright, so you've got f in the notation we did last lecture. So f is a function and it maps from set a to set b. Okay, and g is also a function. These are proper functions, well-formed functions, and g maps set b to c. Right? They're both functions. And h is a function that maps a to c directly. Okay. So h or s x is g of f of x. I'll put it then, because here's the theorem. So then h is a function. Okay, that's the theorem. That's what you're asked to prove. Okay, so you're asked to prove that h is a function. So how do you go about proving that? Well, how do you prove anything is a function? Okay? You have to show that every element in A maps individually to a unique element in C. Okay, so this is theorem 28. So how do you do that? Right. Well, take. Let's not do it verbally, really. Take any element A. So this is a general element, random element in set big A. Okay. Now, you're told that f is a function. Therefore, this A will map to a single element in B. Okay, so you're now here. And G now is also a function. So it will take any element here and map it to a unique element in C. Okay? So in other words, for any element here, you get a unique element in C. A unique element in C. Now F maps all elements from set A into B. Okay, and whatever B is, G is also a function, so it will take all members of big B and map them into C. Okay, so we have a unique mapping from A goes to C, only one, because that's to only one element, and from there to there is only one element. So from here to here is only one element. Okay, and F maps all of these to this set, and G maps all of these to this set, because F and G are both properly defined functions. Okay, so this element here is unique given this one. All right. So you've satisfied the properties of a function. H has the properties of a function. Yeah. Hope you followed that. All right. Okay, so let's have a look at a fairly simple example. Let's say your function f here takes any element x. So what are we doing? We're mapping the reals to the reals. Okay, for this case. So these are your x's, and you're mapping into this set, which is of the form sin x. And then G, whatever, G is second function, it takes whatever's in here and maps it to double the value. So this is also a G maps from real to real. So what would GF be? Now remember, F goes first. You apply F first, so that would take x into sin x, and then G doubles it. So what would GF be? What's its function be? Well, can you see it would just be 2 times sin x? It's sort of